JVM Architecture Explained for Beginners Introduction. JVM stands for Java Virtual Machine. The JVM is the engine that runs Java programs. A Java developer writes public class main, public static void main, string args, system.out.println, hello Java. Java compiler converts it into bytecode. Then JVM runs that bytecode. Simple flow. Java code, Java compiler, bytecode.class file, JVM machine code, program runs. Simple definition. JVM is a virtual machine that runs Java bytecode on any operating system. That is why Java is called write once, run anywhere, because Java code is compiled into bytecode, and the JVM for each operating system runs that bytecode. Example: same java.class file, Windows JVM, Linux JVM, macOS JVM. Why JVM matters. As a Java backend developer, JVM knowledge helps with
performance debugging, memory issues, garbage collection, thread issues, application startup, production monitoring, Spring Boot tuning, out-of-memory error debugging, high CPU debugging, interview preparation. For Spring Boot developers, JVM is very important because every Spring Boot app runs inside the JVM. JVM big picture Java source code, down, compiler javac, down, bytecode.class, down, class loader, runtime data areas, execution engine, native interface, operating system. Main JVM components. 1. Class loader. 2. Runtime data areas. 3. Execution engine. 4. Garbage collector. 5. Java native interface. Native method libraries, JVM architecture diagram, Java source code, Java compiler, .class bytecode, plus rcode, JVM, plus col, plus class loader, plus class loader, plus class loader, plus class loader, plus runtime data areas, plus method, area, metaspace, area heap, stack, PC register, native method stack, plus one, area PC, plus one, execution engine, interpreter, JIT compiler, garbage collector, plus one, plus is INI, JNI plus native libraries, plus is INI. Operating system, step 1, Java source code. You write Java source code. Example: public class hello world, public static void main, string args, system out println hello JVM, file hello world.java. This is human readable Java code. Step 2, Java compiler. The Java compiler is javac. It converts Java source code into bytecode. Command jvac hello world.java. Output hello world.class. The .class file contains bytecode. Step 3, bytecode. Bytecode is intermediate code that JVM understands. It is not direct machine code. Simple idea. Java code is for developers. Bytecode is for JVM. Machine code is for CPU. Flow. Hello world.java. jvac hello world.class. JVM program runs. Step 4. Class loader. The class loader loads .class files into JVM memory. Simple definition. Class loader loads Java classes when the program needs them. Example:
User service equals new user service. Before JVM can use user service, the class must be loaded. Class loading flow. Loading dash. Linking dash. Initialization class loading process. 1. Loading. JVM finds and loads the .class file. User service.class loaded into JVM. 2. JVM verifies and prepares the class. Linking has 3 parts: verification, preparation, resolution. 3. Initialization. Static variables and static blocks are executed. Example. Class app config, static string app name equal demo app. Static system out println app config initialized. When class initializes, static variable assigned static block executed. Class loader types. Common class loaders. Class loader purpose. Bootstrap class loader loads core Java classes. Platform class loader loads platform classes. Application class loader loads application classes. Simple idea. Bootstrap means Java core classes. Platform means Java platform libraries. Application means your app classes. Example. Java lang string means bootstrap your com.example.product service means application step 5, runtime data areas. Runtime data areas are JVM memory areas used while the program runs. Main areas. 1. Method area, metaspace. 2. Heap. 3. Stack. 4. PC register. Native method stack. JVM memory areas diagram. Plus. JVM memory. Method area metaspace. Class metadata. Method metadata. Static info. And heap. Objects. Arrays. Java stack. Method calls. Local variables. Stack frames. PC. Register. Current instruction address. Native method stack. Native method calls. Plus. Step 6. Method area, metaspace. Metaspace stores class level information. It stores class metadata, method metadata, field metadata, runtime constant pool, static information. Example. Class product, private, long-eyed, private string name, public string get name, return name, IFF. Metaspace stores information like class name, product, fields, ID, name, methods, get name. Important. Objects are not stored in metaspace. Class metadata is stored in metaspace. Step 7. Heap memory. Heap is where objects are stored. Example. Product equals new product. The product object is created in heap memory. Simple idea. New keyword usually creates object in heap. Heap stores objects, arrays, instance variables. Example. User equals new user John. Order equals new order. Int 10 nums equals new int 10. These are stored in heap. Heap diagram. Heap. User object, product object, order object, int array, and string objects. Stack stores method calls and local variables. Each thread has its own stack. Example. Public void process order. Int count equals 10. Calculate total count. Public void calculate total int count. Int tax equals 5. When process order is called, stack frame created for process order. When calculate total is called, stack frame created for calculate total when method finishes. Stack frame removed. Stack diagram thread stack. Plus. Calculate total frame. Count equals 10. Tax equals 5. Plus. Process order frame. Count equals 10. Plus. Main frame. Plus. Heap versus stack. Feature. Heap stack stores objects, method calls, local variables, shared across threads, one per thread. Memory cleanup, garbage collector, automatically when method ends. Error, out-of-memory error, stack overflow error. Example, new user, local variable int x. Important example. Reference versus object. User equals new user John. Memory. User variable means stack. User object means heap. Diagram. Stack, heap, plus, user ale, plus, user John. The variable user stores a reference. The actual object is in heap. Step 9. PC register. PC means program counter. PC register stores the address of the current JVM instruction being executed by a thread. Simple idea. PC register tells JVM what instruction to run next. Each thread has its own PC register. Step 10. Native method stack. Native method stack is used when Java calls native code. Native code means code written in languages like C or C++. Example: Java native interface. Most beginner Java developers do not directly use this daily, but it exists inside JVM architecture. Step 11. Execution engine. Execution engine runs the bytecode. It includes 1. Interpreter. 2. JIT compiler. 3. Garbage collector. Simple flow. Bytecode, execution engine. Machine code, step 12, interpreter. Interpreter reads bytecode line by line and executes it. Simple idea. Interpreter executes bytecode one instruction at a time. Benefit. Check starts quickly. Drawback. Can be slower for repeated code. Step 13. JIT compiler. JIT means just-in-time compiler. JIT improves performance by converting frequently executed bytecode into native machine code. Simple idea. Frequently used code becomes optimized machine code. Example: for int I equals 0, I less than 1 million, I++. Calculate. If calculate runs many times, JIT may optimize it. Interpreter versus JIT feature. Interpreter JIT compiler runs bytecode line by line, converts hot code to machine code. Startup, faster startup, optimizes after running. Performance, slower for repeated code, faster for repeated code. Purpose, start execution, optimize execution. Simple idea. Interpreter starts the program. JIT speeds up hot code. Step 14, garbage collector. Garbage collector automatically removes unused objects from heap memory. Example: public void create user. User equals new user John. When method ends, if no reference points to the user object, it becomes eligible for garbage collection. Important: garbage collector frees heap memory. You do not manually delete objects in Java like C, C++. Garbage collection, simple flow. Object created in heap. Object used by application. No references point to object. Object becomes garbage. Garbage collector removes it. Memory becomes available. Step 15. Object eligibility for GC. Example: user equals new user John. User equals null. Now, user object has no reference, so it is eligible for GC. Another example: public void process. User is new user Mary. After method ends, local reference is gone. Object may be eligible for GC. Step 16. Heap generations. Modern JVM heap is usually divided into generations. Common areas: young generation, old generation. Young generation. New objects are created here. Old generation. Long living objects move here. Simple flow. New object, young generation, survives multiple GCs. Old generation, young generation. Young generation usually contains Eden survivor spaces. Simple flow. Object created in Eden. Minor GC happens. Surviving objects move to survivor. After surviving enough GCs, move to old generation. Old generation stores objects that live longer. Example: F. Application level cache, singleton beans, long-living spring beans, static references, persistent collections. If old generation fills up, major GC, full GC may happen. Full GC can be expensive and may pause application. Step 17. Common garbage collectors. Common JVM garbage collectors: serial GC, parallel GC, G1 GC, ZGC, Shenandoah. For many modern Spring Boot applications, G1 GC is commonly used by default in recent Java versions. Beginner explanation. Garbage collector manages heap memory automatically. Different GC algorithms optimize for throughput, latency, or memory behavior. Step 18. JVM threads. Each Java thread has its own stack, its own PC register, but threads share. Heap metaspace. Diagram. Thread 1 stack, thread 2 stack, thread 3 stack, down, down, plus unparalleled thread 2 stack, down, down, plus shared objects, plus. Important. Objects in heap can be shared by multiple threads. That is why thread safety matters. Step 19. JVM and Spring Boot. Spring Boot application runs inside JVM. Flow. Spring Boot jar, snap, JVM starts, classes loaded, Spring context created, beans created in heap, application starts.
Example.
At service, public class, product service. Spring creates a bean object. That bean object lives in heap. Class metadata for product service lives in metaspace. Spring Boot memory example. Metaspace. Product service class metadata, product controller class metadata, order repository class metadata. Heap. Product service bean object, product controller bean object, order repository proxy object, HTTP request objects, DTO objects, entity objects. Stack. Controller method calls, service method calls, repository method calls, local variables. Step 20. JVM startup command. Run Java app. Java-jar app.jar. With heap settings. Java-xms512m-xmx1024m-jar.jar. Meaning. Minus XMS 512 means initial heap size 512 megabytes. Minus XMX 1024 means maximum heap size 1024 megabytes. Common options. XMS means initial heap size. XMX means max heap size. XSS means thread stack size. Step 21. Out-of-memory error. Out-of-memory error happens when JVM cannot allocate required memory. Common types. Java.lang out-of-memory error. Java heap space. Java.lang out-of-memory error. Metaspace. Java.lang out-of-memory error. Unable to create native thread. Java heap space error. Example, cause. List byte a list equals new array list, while true. List add new byte 1024 times 1024. Problem. Objects keep getting added. Heap fills up. GC cannot free memory. Out-of-memory error happens. Fix ideas. Check, remove unused references. Check, reduce memory usage. Check, use pagination streaming. Check, avoid loading huge data at once. Check, memory leak. Check, increase heap only if needed. Metaspace error. Metaspace error happens when too much class metadata is loaded. Possible causes. Too many dynamically generated classes. Class loader leaks. Repeated redeployment issues. Proxy class generation problems. Error. Java.lang.outofmemoryError. Metaspace StackOverflowError. StackOverflowError happens when stack memory is exhausted. Common cause. Infinite recursion. Example. Public void call. Call. This keeps adding stack frames until stack overflows. Error. Java.lang.StackOverflowError. Fix. Comma. Add base case. Avoid infinite recursion. Convert to loop if needed. Step 22. JVM monitoring tools. Useful tools. JPS, JStack, JMap, JCMD, JConsole, Visual VM, Java Flight Recorder, Mission Control, GC Logs, Actuator Metrics, APM tools. Common usage. High CPU means thread dump with JStack. Memory issue means heap dump with JMap, JCMD. GC issue means GC logs. Spring Boot metrics means actuator. Production monitoring means Dynatrace, AppDynamics, New Relic. Thread dump shows what threads are doing. Use for high CPU, deadlocks, stuck threads, blocked requests, slow application. Example command. JStack PID. In production, you usually collect thread dumps safely using approved tools processes. Step 24. Heap dump. Heap dump shows objects in heap memory. Use for exclamation marks, large object analysis, out-of-memory error, unexpected memory usage. Example command. jmap dump format b file heapdump.hprof analyze with Eclipse NAT Visual VM JDK mission control. Step 25. GC logs. GC logs show garbage collection behavior. Use for dot. Check long pauses, frequent GC, memory pressure, heap tuning, latency issues. Example JVM option. Xlog GC. GC logs can answer. How often is GC running? How long are pauses? Is heap filling quickly? Are objects moving to old generation? Is full GC happening? JVM Architecture Summary Flow. 1. Developer writes Java code. JavaC compiles Java code to bytecode 3. JVM starts 4. Class loader loads classes 5. Runtime data areas store data 6. Execution engine executes bytecode 7. Interpreter starts execution 8. JIT optimizes hot code 9. Garbage collector manages heap memory 10. Program runs on operating system. Common beginner mistakes 1. Thinking JVM runs Java source code directly. Wrong. JVM runs .java files directly. Correct. JVM runs bytecode from .class files. 2. Confusing JDK, JRE, and JVM. Simple difference. JDK equal tools for developers. JRE equal environment to run Java. JVM equal machine that runs bytecode. Modern Java distributions often package runtime and tools differently, but this concept is still useful for beginners. 3. Thinking objects are stored in stack. Wrong. Objects are stored in stack. Object references can be in stack. Objects are stored in heap. Example. User equals new user. User reference means stack. User object means heap. 4. Ignoring garbage collection. Bad assumption. Java handles memory, so memory issues never happen. Reality. Java has automatic GC, but memory leaks can still happen if references are kept. Example. Static list keeps growing forever. 5. Increasing heap without finding root cause. Out-of-memory error happened. Just increase -x and x. Better. Check heap dump. Find what consumes memory, then decide whether to fix code or increase memory. 6. Confusing stack overflow error with out-of-memory error. Stack overflow error. Too many method calls / recursion. Out-of-memory error. Heap metaspace native memory problem 7. Not understanding thread memory. Each thread has its own stack. Too many threads can cause. Unable to create native thread best practices. Understand heap versus stack. Know where objects are stored. Know class loading basics. Understand bytecode concept. Monitor heap usage. Monitor GC behavior. Avoid loading huge data into memory. Use pagination for large database results. Avoid unnecessary static collections. Collect heap dumps for memory leaks. Collect thread dumps for high CPU, stuck threads. Tune JVM only after measuring. Set reasonable XMS and XNX for production. Use Spring Boot actuator metrics. Learn basic GC logs. Understand JIT at a high level. JVM interview questions. 1. What is JVM? JVM is Java Virtual Machine. It runs Java bytecode and allows Java programs to run on different operating systems. 2. What does JVM run? JVM runs bytecode from .class files. 3. What is bytecode? Bytecode is intermediate code generated by the Java compiler and executed by the JVM. 4. What is class loader? Class loader loads Java class files into JVM memory. 5. What are JVM runtime data areas? Common areas are method area, metaspace, heap stack, PC register, native method stack. 6. What is heap memory? Heap memory stores objects and arrays. 7. What is stack memory? Stack memory stores method calls, local variables, and stack frames. 8. Heap versus stack. Heap stores objects and is shared across threads. Stack stores method frames and is private to each thread. 9. What is metaspace? Metaspace stores class metadata. 10. What is garbage collection? Garbage collection automatically removes unused objects from heap memory. 11. What is JIT compiler? JIT compiler converts frequently used bytecode into optimized native machine code during runtime. 12. What is interpreter? Interpreter executes bytecode instruction by instruction. 13. What causes out-of-memory error? It happens when JVM cannot allocate required memory, commonly because heap, metaspace, or native thread memory is exhausted. 14. What causes stack overflow error? Usually infinite recursion, or too many nested method calls. 15. What is -XMX? -MMX sets maximum heap size. Example: XMX 1024M 16. What is -XMS? XMS sets initial heap size. Example: XMS 512M 17. What is a thread dump? A thread dump shows the state and stack trace of running threads. 18. What is a heap dump? A heap dump is a snapshot of objects in heap memory. 19. How do you debug memory leak? Typical steps. 1. Check memory metrics. 2. Enable and inspect GC logs. 3. Capture heap dump. 4. Analyze largest objects. 5. Find references keeping objects alive. 6. Fix code or configuration. 20. How does JVM help Java run anywhere? Java code is compiled to bytecode. JVM implementations exist for different operating systems and run the same bytecode. JVM roadmap, beginner level. Learn. Check JDK, JRE, JVM, Java compiler, bytecode, class loading, heap, stack, garbage collection basics. Practice. Compile Java file using Java. Run class using Java. Understand .java and .class files. Intermediate level. Learn. Practice. Run Spring Boot app with XNS and XMX. Check memory usage. Generate simple thread dump. Advanced level. Learn. GC tuning, GC logs, memory leak analysis, JFR, JDK mission control, class loader leaks, performance profiling, thread contention. Practice. Analyze heap dump. Analyze GC logs. Debug high CPU using thread dump. 30-day learning plan. Week 1. JVM basics. Learn. What is JVM? Check what is bytecode. Check Java. Check Java command. JDK versus JRE versus JVM. Practice. Create hello-world.java. Compile with Javac. Run with Java. Inspect.class file conceptually. Week 2. JVM memory. Learn. Heap, stack, metaspace, PC register, native method stack, object reference, method frames. Practice. Draw a memory diagram for simple Java methods. Explain where object and reference are stored. Week 3, execution and GC. Learn. Check interpreter. Check compiler. Check garbage collection. Check young generation. Check old generation. Check out-of-memory error. Practice. Write small recursion example. Write object creation example. Understand why GC happens. Week 4, production debugging. Learn. JVM options. XMS, XNX, XMX, JStack, JMap, JCMD, GC logs, heap dump, thread dump. Practice. Run Spring Boot app with JVM options. Check process ID with JPS. Learn what thread dump and heap dump are used for. Real-world Spring Boot example scenario. Product API memory issue. Application. Spring Boot Product API. Problem. API becomes slow and memory keeps increasing. Possible cause. Private static final list, product response, cache, equals new array list. If this list keeps growing and never clears, objects remain referenced. GC cannot remove them. Heap usage increases. Out-of-memory error may happen. Debug approach. 1. Check heap memory metrics. 2. Check GC frequency. 3. Capture heap dump. 4. Find large array list. 5. Check why references are retained. 6. Fix cache design. 7. Use proper cache like caffeine/Redis with TTL. Real-world high CPU example. Problem. Spring Boot app CPU is very high. Possible causes. Infinite loop. Too many threads. Expensive computation. Blocking issue. GC pressure. Bad algorithm. Debug approach. 1. Find Java process ID. 2. Capture thread dump. 3. Identify busy thread. 4. Check stack trace. 5. Find code causing CPU usage. 6. Fix logic or optimize algorithm. Real-world GC issue example. Problem. API response time randomly spikes. Possible cause. Full GC pauses. Debug approach. 1. Enable GC logs. 2. Check pause duration. 3. Check heap usage before/after GC. 4. Find allocation-heavy code. 5. Tune heap GC if needed. 6. Reduce unnecessary object creation. Must-know JVM topics. 1. JDK versus JRE versus JVM. Java compilation process. 3. Bytecode. 4. Class loader. 5. Heap. 6. Stack. 7. Metaspace. 8. Execution engine. 9. Interpreter. 10. JIT compiler. 11. Garbage collection. 12. Young generation. 13. Old generation. 14. Out-of-memory error 15. Stack overflow error 16. Thread dump 17. Heap dump 18. GC logs 19. JVM options 20. Spring Boot JVM tuning basics. Final summary. JVM architecture is the foundation of Java application execution. Important components. Check. Class loader. Runtime data areas. Heap. Stack. Metaspace. PC register. Native method stack. Execution engine. Interpreter. JIT compiler. Garbage collector. JNI. Key idea. Java code is compiled into bytecode. JVM loads, verifies, executes, optimizes, and manages memory for that bytecode. For backend developers, understanding JVM helps debug memory, performance, GC, threads, and production issues. For interviews, explain JVM using class loading means memory areas, means execution engine, means garbage collection.